Hello and welcome you all to this session of heat power engineering. Today we shall start a new module which is based on the properties of gases and the laws of thermodynamics. So in this module we shall discuss all the laws of thermodynamics as well as the properties of real and ideal gases. We will study In this lecture session, we will study basically the properties of gases. We will try to understand what are the difference between an ideal gas and a real gas. How do they behave in different thermodynamic processes, and what are the functional relationship between the different properties that distinguish these ideal gases from that of the real gases. And then we shall see the properties like specific heats, and we'll study the relations between them for an ideal gas. So let us start our discussion on the properties of gases. So these are the lecture objectives. First of all, we'll start to understand the equations of state for ideal gases. We'll try to study the functional relationships between the various parameters like pressure, volume, or temperature for an ideal gas. Then with this understanding, we shall proceed towards the differences between the perfect and real gases. Okay, and then we will try to understand the concept of gas constants. We will try to describe what do we mean by characteristics, gas constant, and universal gas constant. We will also learn how does they go on changing, and then we will study the concept of specific heats. So specific heat at constant pressure and specific heat at constant volume. What do we mean by those specific heats? And we'll try to find the various relationships that exist between them. So let us start our discussion from the equation of state for ideal gases. So I believe most of you have the understanding of the ideal gas or the real gases because you have studied these concepts in your earlier classes in your school level, I believe. But still, we need to study these ideal gases from a different perspective, and that is from the thermodynamic point of view. So when we are studying from the thermodynamic point of view, we must understand that for any compressible system, that means the system which is able which is somehow getting compressed to give us the desired output. So for any compressible system, there there always exists a fundamental relationship between pressure, volume, and temperature. Okay, so for any compressible system, there exists a functional or fundamental relationship between these three parameters: pressure, volume, and temperature. Remember, pressure, volume, and temperature are the measurable properties, as well as it can be sensed also. Okay, so these three properties are very important for a compressible system, and any compressible system can be functionally defined by the virtue of these three specific properties, and they are related in such a way so that we can write PdT, function of PdT is equal to 0. That means if there is a certain function which is comprised of these three parameters, then they can be expressed in this format. Now, the this concept is known as equation of state. The equation of state. Okay, so f of pressure, function of pressure, volume, and temperature is equal to 0. So this is known as the equation of state. Now what is the equation of state for the ideal gas? That defines an ideal gas and its behaviors in the various pressure ranges and temperature ranges. Now, the equation of ideal gas can be considered in this way. It is PV is equal to mRT. Okay, so PV is equal to mRT. I believe you know these things very well. What is this P? P is the pressure, V is the volume. Sometimes we may also refer it as specific volume. This m is the mass of the gaseous system, r is the gas constant, and T is the temperature of the system. Okay, now so this is the equation. This is the equation for an ideal gas. Okay, so you can also define the ideal gases in such a way that ideal gases are those gases which obey, which maintain this functional relationship PV equal to mRT. So the gases which follow the law of PV equal to mRT can be called as ideal gases. Now the gases which doesn't follow the law of PV equal to mRT at different pressure ranges and temperature ranges, they are termed as real gases. So obviously real gases doesn't follow the law of PV equal to mRT at all pressure and temperature ranges. Now there is obviously a certain assumption that when this this pressure tends to zero, that means the pressure is very low, the pressure is very low, or you can say when the pressure is very low or the temperature is very high, these real gases would behave like an ideal gases. So these real gases would conform to the ideal gases when this pressure is very low or temperature is very high. Now there are some assumptions which has made this concept of ideal gases very easy to understand. Okay, so it is the kinetic theory of gases. There are some fundamental assumptions. By virtue of that, we had been able to define the concept of ideal gases. So while defining ideal gases, we have always considered that the molecules which are in random motion. Okay, so the gaseous molecules which are in random motion, they are colliding with each other. You know the concept of Brownian motion, and you can say we had assumed that the molecules are point masses. Okay, so the molecules are point masses. So it means that there is absolutely no mass of the molecule which is being considered. Okay, so the the molecules doesn't have any mass which should be calculated while defining the concepts or the laws of ideal gases. So the mass has been neglected. Okay, the mass of the gaseous molecules have been neglected. Okay, that means they are considered as point masses. And now there is no cohesive forces, no forces of attraction between these molecules. Okay, so the second assumption is that there is no existence of cohesive forces. You know what is cohesive force? Cohesive force, you know the similar kind of molecules which are the force by which the similar kind of molecules are attracted towards each other. Okay, that is the cohesive force. Now this cohesive force practically they though exist in the analysis of the gases, but for the uh, assumptions during the kinetic theory of gases, it had been assumed that there is no existence of or no presence of cohesive forces. Okay, cohesive forces, no cohesive forces, or no forces of attraction. So no cohesive forces, no cohesive forces, no cohesive forces, and no forces of attraction. No forces of attraction between the gas molecules. Okay, so these are the three assumptions. You can say the gas molecules are considered as point masses, the first and the fundamental assumption. Then we assume that there is no presence of cohesive forces or forces of attraction, and this statement number 3 is a direct consequence of this assumption. So as there is no forces of attraction, the gas molecules are moving always in a linear direction. Okay. Now the real gases only follow the laws of ideal gases at low pressures and high temperatures, and except these low pressures and high temperatures, the real gases does have different law. Okay, so they obey different other laws, like the most prominent law is the van der Waals law, which we define as van der Waals law. Okay, so the statement of van der Waals can be written as P plus A by V square, P plus A by V square into V minus P is equal to MRT. P plus A by V square into V minus B is equal to MRT. So here you can see this A by B square term is added and this minus B term is being also incorporated in this equation. Now this A by B square is a term which cohorts or conforms to the presence of cohesive forces. Now if you address the cohesive forces which are obviously present within the gas molecules, then this A term defines the presence of these cohesive forces. And when you don't consider the gas molecules as point masses, don't consider the gas molecules as point masses, then obviously these gas molecules should have some mass which should be deducted, and this B is that value. Okay, so this P is the mass of the gas molecules which is being incorporated in this law, and thus this is the statement of the van der Waals law. Now this law is valid for the perfect or real I'm sorry, this law is valid for the real gases. Okay, and this is the ideal gas statement. Okay, now let's see a different statement or a different representation of the same law which is given here. So let us see that by the Avogadro. Now in chemistry of your school level chemistry, you have studied that the number of moles means the mass of the gas divided by the molecular weight. Okay, now here you can see the 64 kg of oxygen. Okay, so what is the number of moles for this mass of oxygen? It would be obviously 64 divided by the molecular weight. And what is the molecular weight of oxygen? It is 32. Okay, so the molecular weight of oxygen is 32. That means it would give you 2 moles. Okay, or you can say 2 kg mole. 2 kg mole. Okay, so that is how we can define the number of moles for any gas. Similarly, the 36 kg of H2O can also be represented as 2 kg moles of uh, water. Okay, now if we apply this law, if we say that N is the number of moles which is equal to M by M, M being the mass and capital M being the molecular weight, and if we put the value of this M in this equation which we had done for the ideal gas, we had seen the equation of ideal gas can be written as PV equal to MRT, where M refers to the mass of the ideal gas. And now if we write that PV is equal to N into M. Okay, N into M, N equal to M RT. Okay, very simple thing, N into M RT. Then what will happen? This equation can be rearranged in such a way so that we can write P into V divided by N equal to MR into T. Okay, so now rewriting this V by N as V bar and rewriting MR as R bar, we can rewrite the same equation, but in a little bit of different way, and that is PV bar is equal to R bar T. Okay, so this also represents the equation of ideal gas. So this is Avogadro's law for you, and you can see that this B bar represents the uh, molecular specific volume and or the molar specific volume to specific. So this is molar specific volume, and this R represents the universal gas constant. Okay, so this is molar specific volume for you, and this R is nothing but the universal. This is universal gas constant. Okay, so this is universal gas constant. Okay, so this R bar is represented as the universal gas constant. Now you must remember the value of this universal gas constant. You have to remember the value of this universal gas constant, and it is 8.31. 8 point for your engineering life. You should remember the value of this universal gas constant. This is kg mole Kelvin. So 8.31 kilojoule per kg mole Kelvin. Okay, this is the value of the universal gas constant. So now it is quite evident. So now we have these two important statements for an ideal gases. It is PV. It is PV equal to RT and PV bar equal to R bar T. So PV equal to MRT. This is the first statement. Okay, this is PV equal to MRT, and for the mass of 1 kg it can be written as PV equal to RT, and this is the second statement. PV bar is equal to R bar T. Okay, so this is the two statements of an ideal gas. Okay, so I believe now you have no problem understanding the difference between these two statements. Now with this we have already defined this R bar as the universal gas constant. So when this R bar or 8.314 is being divided by the molecular weight, it is defined as a characteristic gas constant. So the universal gas constant divided by the molecular weight can be represented as characteristic gas constant. Like for O2, so you can write R O2. So this is the characteristic gas constant for O2. It will be 8.31 divided by 32. Similarly, for our H2O, it can be represented as uh, 8.31 divided by 36. Okay. So therefore, you can understand how we are able to distinguish the characteristic gas constant and the universal gas constant, and these are the statements of ideal gas laws, and you can easily understand the difference between these two statements. And you must remember that when this volume is tending towards infinite, or the pressure is very low, or you can say in other words, temperature is very high. Okay, very high, then the statements, all the real gases would follow this law. Okay, so you can use the calculus a little bit here, writing like this: P tending towards 0 and V tending towards infinite. Here V bar can be written as R bar Okay, so when the pressure is very low and the volume is very high, all the real gases would behave like an ideal gas. Okay, so with this understanding, let us move on to the next topic, where we will discuss the specific heats and what do we mean by the specific heats for an ideal gas. So let us see that. So now we will discuss specific heats for an ideal gas. Now for an ideal gas, specific heat can be described when we had described the concepts of first law of thermodynamics. It is better to explain from the point of view of first law of thermodynamics because it involves some thermodynamic property. We will see the specific heats in another way in the next lecture session, but better to discuss specific heat. A primitive approach can be provided to you so that you understand what the specific heats at constant pressure and what the specific heat at constant volume actually mean. So we can consider the amount of heat which is required to increase the temperature by 1 degree Celsius for a 1 kg of an ideal gas. That is called as the specific heat at constant pressure. So keeping the pressure constant, if you want to increase the temperature of 1 kg ideal gas by 1 degree Celsius, then the heat transfer which is required, that is called as the specific heat at constant pressure. Similarly, if you want to increase the temperature by 1 degree Celsius for 1 kg of an ideal gas, uh, keeping the volume constant, then this would be called as the specific heat at constant volume. Okay, so it is quite obvious that when this mass becomes 1 kg, delta T becomes 1 degree Celsius, then what is the heat required to increase the temperature by 1 degree Celsius? That is the heat transfer, which we call as specific heat at constant pressure. Now for air, it is 1.005 kilojoule per kg Kelvin. Okay, kilojoule per kg Kelvin. I would request you to remember these values very well, because for uh, for an ideal gas, you will see. So this is Cp for air. Okay, I'm sorry that I had told that this is the value of Cp for an ideal gas, but let me correct. This is the specific heat at constant pressure for air. Okay, this is for air because as we use air in different heat engines, you will see later on. So you please remember this value of Cp for air, and you should also remember the value of Cv for air also. Okay, you will see later on in the later discussions for Otto cycle, diesel cycles. You will see air is a very important working fluid, and the Cv is defined as 0.718 kilojoule per kg Kelvin. Okay, so always remember these two factors. And in the next class, when we will be discussing the first law of thermodynamics, we will see how we can define Cp and Cv for uh, an ideal gas from the thermodynamics perspective. So this is entirely defined from the perspective of basic heat transfer concept. But in the next class, we will see and discuss the concept of Cp and Cv for an ideal gas or for all substances from the thermodynamics point of view or the heat power perspective. Okay, so now with this, let us move on to discuss the concepts of adiabatic index. Okay, so before that, you must remember the Cp and Cv, they are related by these two important statements. So the Cp minus Cv is equal to R. Okay, so Cp minus Cv is equal to R, and Cp by Cv is equal to gamma. Okay, so these are the two important relationships between the specific heats for an ideal gas. Now, for an ideal gas, you will see, you have already seen that for air it is 0.1.005 and Cv is 0.718. So R for an ideal gas would become 0.287 to 0.287, kilojoule per kg Kelvin. Okay, now coming on to the topic, which is our main focus over here. Cp by Cv is equal to gamma. Now what is this gamma? Gamma is the adiabatic index. Now you have already seen when we had defined the concept of adiabatic process where there is no heat transfer, this PV gamma is equal to constant. So this is the statement by which an adiabatic process can be defined, and you must understand that this process is something where there is no heat transfer, and this is the functional relationship between pressure and volume. Okay, now for an ideal gas, this functional relationship between pressure and volume can be described in terms of volume and temperature as well as pressure and temperature. We will now see how this statement can be modified to express the functional relationships between volume and temperature as well as pressure and temperature. Okay, so for an ideal gas, you know that PV is equal to RT. We have already seen that PV is equal to RT. Okay, so we are not writing the M over here. You can assume that we are doing this deduction for 1 kg of the gas. Okay, so PV is equal to RT. Now, if you replace P as RT by V over here, if you replace P equal to RT by V, so you can easily say that P is equal to RT by V, and putting the value of P RT by V over here, you can write, so I will use a different color here. So here you can write RT by V into V to the power gamma is equal to constant. Okay, so it becomes, you know that R is itself a constant. So if you rearrange by putting this R on the other side, so it will become C by R, so it will generate a new constant. So nothing to worry about this. And if we transform this equation in this format, so we can say that T into V to the power gamma minus 1 becomes a constant. Okay, so as PV to the power gamma equal to constant, there is T into V to the power gamma minus 1 is equal to constant. So this represents the functional relationship between pressure and volume, and this represents the functional relationship between temperature and volume. Suppose in a mathematical problem, it has been given the temperature changes from 100 Kelvin to 200 Kelvin or 300 Kelvin to 400 Kelvin. The volume initially was let us say 0.03 kg per meter cube. Okay, sorry, meter cube per kg. It was initially given. So the volume was 0.03 meter cube or meter cube per kg if we are dealing with specific volume. Then what is the final volume? Then you can easily follow this statement. You can write the equation like this: T1 into V to the power 1 gamma minus 1 is equal to T2 into V to the power gamma minus 1. So putting values of T1, T2, V1, you can easily get this T2. Now the question is, what is the value of this gamma for an ideal gas? So it would obviously depend on the nature of the ideal gas which we are speaking about. So gamma always depends on the atomicity of the gas. Okay, so if it is an diatomic molecule, which air is, and we take air, for air gamma as 1.4. So for diatomic molecules, gamma is taken as 1.4. So always remember the value of gamma, and generally we are used to uh, used used with air as an working fluid. So generally you will see gamma is put as 1.4. Now if the concerned gas is different and its atomicity is different, it is a single molecular gas or trimolecular gas, then obviously the value of gamma would change, and that would be given in your problem. Okay, so atomicity, depending on the atomicity of the gas, it this gamma changes. Okay, so we have seen the pressure volume relationship, the temperature volume relationship, and now let us try to find out the functional relationship between pressure and temperature when an adiabatic process is being carried out. So if you write V as if you write V as T by P, then what you will find here, P, putting the value of V in this equation, in this fundamental equation of an adiabatic process. So you will see it will be P into R T by P, R T by P equal to constant. Now it is obvious that R to the power gamma would also remain as a constant, so nothing to worry about that. And if you modify the equation, then you can write T to the power gamma divided by T to the power gamma minus 1 is equal to constant. Okay, so here this equation can be modified this way: T to the power gamma divided by T to the power gamma minus 1 is equal to constant. So here you can see the pressure volume relationship, the temperature volume relationship, and the temperature pressure relationship. So in all of this equation you can see this gamma over here. So this gamma is nothing but Cp by Cv. For air it is taken as 1.4, and gamma always depends on the atomicity of the gas. Okay, so gamma can vary if the concerned gases are different, their atomicity is different. Okay, so with this we would like to end this lecture here. In the next lecture we will start discussing about the concepts of first law of thermodynamics. So till then, goodbye and thank you for your time.